Hey Calc friends, this is AP Calculus section 5.8 notes. When we first started talking about integration and area under the curve, we began our exploration by looking at estimating the area under the curve using rectangles, left endpoints, right endpoints, midpoints. And we talked about, curvy functions, we usually use rectangles, whereas if we had a function that was kind of a bunch of linear segments, maybe we could use triangles or trapezoids or things like that to estimate the area under the curve. Always, thinking that this is a method that we would use if we didn't have a function that we could integrate specifically, or, we didn't know what the function was, we just had a picture, right? Well, today we're going to kind of come back full circle. We're going to go back to where our integration journey started here with the area under the curve, and we're going to think about, well, what if, we don't have a function? What if we have data that is just represented by a graph or a picture, and we're trying to find the area under the curve? How can we use different methods to approximate the integral or approximate the area under the curve besides the ones that we already know? Now, we're going to learn a few new methods today, and to kind of compare how good those methods are, we're going to use a function that we know, a function that we can evaluate exactly the area under the curve, so that as we are estimating it using different methods, we have a basis of comparison against the real, actual, exact value. So to compare methods, we are going to calculate the integral from 1 to 2 of the function 1 over x dx. And this integral can be easily calculated, so we can compare the exact value to what we get using our different approximations. So in our example 1 here, first we're going to start out today by just finding the value of this integral. And we know that 1 over x is the derivative of natural log x, so therefore the integral of 1 over x would be ln x, right? So this is going to be equal to ln, absolute value of x, of course, on the integral from 1 to 2. And if we were to evaluate this at our limits of integration, right, so using the evaluation theorem, this would just be natural log 2 minus natural log 1, which if you type that in your calculator and you round your answer to 3 places past the decimal per AP rules, the exact value of our integral from 0 to 1 is 0.693. Okay, and this is an exact value of this integral from 1 to 2. So the approximation methods that we use today to evaluate this, we're going to be comparing to this exact value to see how close they might get. All right, so we are going to start with some processes that we are already familiar with, our left endpoint rectangles and our right endpoint rectangles. So example 2 says use left and right endpoints and n equals 5 to approximate the integral from 1 to 2 of 1 over x dx, and then tell if they are underestimates or overestimates to the actual area and why. All right, so first of all, let's find our delta x. So we know that our delta x is going to be based on our limits of integration, the distance between them divided by 5, right? So we have the same picture here for both. And again, if we're going from 1 to 2, this would be like 1.0 here, and this would be like 2.0 on both of our pictures. And we want to divide our interval from 1 to 2 into 5 equal rectangles. So our delta x for both of these is going to be 2 minus 1, right, b minus a, 2 minus 1 divided by 5, which is 1/5 or 0.2, right? So then each of these distances here is going to be 0.2. So this is 1.2, 1.4, 1.6, and 1.8. And so if I'm using left endpoint rectangles, I will start with that one first. Then the height of my rectangle will be determined by the left corner of the rectangle here. So the height of the first rectangle would be right here, and then the second rectangle would be right here, and the third would be here, the fourth would be here, and the fifth would be there, right? And so these would be the areas that we would be calculating. And obviously we can already see that this is going to be an overestimate, right? Because our rectangles, pieces of our rectangles of our areas lie above our curve. So we know that our area is going to be a little bit more than it should be. So my area here, using left endpoints, is going to approximately be equal to the area of each of my rectangles. And I know that the base of each of them is my delta x. And then for my left endpoints, it's going to be f of 1.0 plus f of 1.2 plus f of 1.4 plus f of 1.6 plus f of 1.8, right? Because those would be the heights on the left side of each of my rectangles. So my delta x is going to be the same. It's going to be 0.2, right? That's the base of each rectangle. And then if I just plug 1 into the function, right? So I am actually plugging that into 1 over x, right? So 1 divided by 1 is going to give me 1. And 1 divided by 1.2, right? That's going to give me my 0.833. So I am just finding the value of the function at x equals 1.0, 1.2, 1.4. I am plugging that into 1 over x, okay? So then f of 1.4 is going to be 0.714. F of 1.6 is going to be 0.625. And f of 1.8 is going to be 0.556. And then I grab my calculator again, I just add all these numbers together and I multiply by 0.2 and I get that my area with left endpoints is going to be approximately equal to 0.746. And I know that this is an overestimate. Because the function is decreasing. On our interval from 1 to 2, right? Our function is decreasing on 1 to 2. All right, so now I am going to calculate the right endpoints. And so my right endpoints, my rectangles should fall below the curve, right? So if I label these, this is 1.2, 1.4, 1.6, and 1.8, just like before. But now the height of my first rectangle is going to be the height of the function at 1.2. And the height of the second rectangle will be the height of the function at x equals 1.4. And my third rectangle, 1.6, and my fourth rectangle, 1.8, and my fifth rectangle, 2.0. So now my areas are a little bit less than the curve, and so I should end up with an underestimate of the exact value, right? And so in generic form this time, my area is approximately going to be equal to my delta x times f of 1.2 plus f of 1.4 plus f of 1.6 plus f of 1.8 plus f of 2.0. And when I evaluate my function at those points along the x-axis, I know that my area is going to be approximately equal to 0.2. There's my base of each of my rectangles. And then I have 0.833 plus 0.714 plus 0.625 plus 0.556 plus 0.5, because 1 divided by 2 is 1/2, so that one's an exact. And simplifying this on my calculator, I get that my area is approximately 0.646 this time. And I know that this is an underestimate. Because the function is decreasing on 1 to 2. Same reason as before. Okay, so we get underestimate here, and we get overestimate here, right? And we have our two answers. Now, it should make sense that our exact value was 0.693, which is between 0.746 and 0.646, right? So we know that we're in the ballpark here with our left endpoints and our right endpoints. But we have already discussed this school year how if we're going to use rectangles, our best estimate doesn't come from left or right endpoints. Our best estimate comes from midpoints. Okay, now the midpoint rule is not perfect, right? And above your midpoint rule box on your paper, you have that other little box that says that note, the midpoint rule gives an underestimate when the function is concave up, and it gives an overestimate when the function is concave down. Okay, so it's still not perfect. However, it's going to be a closer approximation than either left endpoints or right endpoints. So now, let's calculate our area here using the midpoint rectangle rule. So once again, I've got my x-axis divided up into 5 segments here. We've got 1.0, 1.2, 1.4, 1.6, 1.8, and 2.0. But this time, and of course, sorry, my delta x is still going to be the same. It's still going to be 2 minus 1 divided by 5, so it's still 1/5 or my 0.2, right? That hasn't changed. And so my area this time, though, is going to be a little bit different. My area is going to be equal to my delta x times, but now it's going to be the midpoint between f of 1 and f of 2, which is going to be f of 1.1 plus, and then the midpoint between 1.2 and 1.4 would be 1.3 plus, and the midpoint between 1.4 and 1.6 is 1.5 plus, and the midpoint between 1.6 and 1.8 is 1.7 plus, and the midpoint between 1.8 and 2.0 is 1.9. So my heights this time are going to be right in between those markings on my x-axis. And so when I draw my rectangles, just as they've always been, there will be a little bit above and a little bit below, which we assume mostly kind of evens itself out and gives me the best approximation to my area of the 3 types of rectangle approximating that I can do. And so when I figure out what these values are, again, just plugging these x values into 1 over x. So 1 divided by 1.1, 1 divided by 1.3, 1 divided by 1.5, so on and so forth, I get the following values. 0.2 is my delta x. F of 1.1 is 0.909. F of 1.3 is 0.769. F of 1.5 is 0.667. F of 1.7 is 0.588. And F of 1.9 is 0.526. Adding those together and multiplying by 0.2, we get an approximate area of 0.692, which, notice, is our best estimate so far. Right? But we haven't learned anything new yet. I mean, we know that the exact value is 0.693, but as far as approximating area under the curve, left endpoint rectangles, right endpoint rectangles, and midpoint rectangles is all work that we have experienced previously. So now it's time to learn something new. And the first new approximation method that we are going to learn is called the trapezoidal rule. And you can kind of see the picture of it right there to illustrate that basically the trapezoidal rule uses, area approximation by cutting the area up into trapezoids. But what's interesting to note here is that the trapezoidal rule actually comes from averaging the approximation of left endpoint and right endpoint rectangle approximations. So rather than doing the left endpoint rule, doing the right endpoint rule, and averaging them together, you could just do the trapezoidal rule and get the same result. Okay, and we're going to prove that in just a moment. So here's our trapezoidal rule, that our integral can be approximated by taking our delta x divided by 2, and then it's f of x sub 0, x sub 0 being the lower limit of our integral, to, and then times, or plus 2 times f of x1, 2 times f of x2. Again, these are the locations of our x values along our x-axis, however many we have based on our delta x, right? And so there's a pattern here. F of x0 has a coefficient of 1 in front of it. And then notice that all of the values in between have a coefficient of 2 except for the last value in the series, which has a coefficient of 1. And it tells you where delta x is, again, your b minus a divided by n, right? And then your x sub I is your a plus your I times your change in x, which, basically is just how you count or how you divide your interval up, where your heights basically are located, okay? And so I want to put a little note here that the number of values in the parentheses will be n plus 1 due to the formula. It looks complicated, but it really is not, okay? You'll see as we work through the example here. So let's start with our delta x. So once again, here our delta x, this hasn't changed for any of them, is 2 minus 1 divided by, we want to do 5 subintervals, right? So again, this is 1/5 or our 0.2 value. So just generically looking at our formula and trying to write a generic approximation for our area is going to be approximately equal to our delta x, which is 0.2 divided by 2 times, and then it's the lower endpoint, so f of 1 is our lower endpoint, plus, and then again, we're just adding that delta x on, right? So 0.2, so 1.2 will be next one, but it has to be 2 times f of 1.2, 2 times f of 1.4, 2 times f of 1.6, 2 times f of 1.8, and then plus f of 2.0. So you use both endpoints, the lower and the upper, in the trapezoidal rule, which is different than the left endpoint and right endpoint rectangles, right? And now we just have to plug the values in and do the math. Okay, so my area is going to be approximately equal to 0.2 divided by 2 is going to be 0.1, and then f of 1 is 1. 2 times f of 1.2, well, I already know f of 1.2, I've done that many times. Multiply it by 2, you get 1.667. 2 times f of 1.4 is 1.429, again, keeping everything rounded to 3 places past the decimal. F of 1.6 is going to be 1.250. 2 times f of 1.8 is going to be 1.111, and then f of 2.0 is that 0.500. And then you grab your calculator and you do the math, and you get that the area is approximately equal to 0.696. Okay. Whoops, I'm sorry, I put 693. That's the exact value. 0.696 is what we get here, okay? And so our midpoint rule did get us a little closer because our midpoint rule gave us 0.692 and the exact value is 0.693, but 0.696 is still quite close. And I just want to point something out to you because remember they said that the trapezoidal rule comes from averaging the approximations of your left and your right endpoints together. So if we average L5 and R5 from example 2, that would be 0.746 plus 0.646. If we add those together and divide by 2, guess what we get? 0.696. So doing the trapezoidal rule is basically like doing the average of left-hand rectangles and right-hand rectangles. So it's quite a decent approximation. Okay, we are going to learn one final method for approximating area under the curve, and this is called Simpson's rule. And Simpson's rule actually uses parabolas to estimate the area under the curve. And Simpson's rule says, note that the pattern of the coefficients within the brackets is 1 and then 4, 2, 4, 2, 4, 2, 4, 2, 4, and then you always have to end on the 1. Okay, so it always starts with a 1, 4, and then it goes 2, 4, 2, 4, 2, 4, and then it always ends with a 4, 1 at the end. And again, the number of values in the parentheses will be n plus 1 due to the formula. So I've got that little note to write here. And then the other thing is that Simpson's rule requires our n to be an even number. Because of the way that the pattern of the coefficients has to go, n has to be an even number. So we've been approximating our area with 5 either rectangles or trapezoids. Well, we can't do 5 this time because Simpson's rule requires that we have an even number. So in this case, we're just going to do 4, okay? So I will start with, let's use n equals 4. And this is because n must be even. Okay, so now our delta x is going to change because our n just changed. So our delta x is still going to be b minus a, so 2 minus 1, but this time divided by 4. So we end up with 1/4 or 0.25 for our delta x this time. And so our area, according to Simpson's rule, is going to be approximately equal to, we'll call it S sub 4, since we're doing 4 subsegments of parabolas here. And the rule says that you've got your delta x divided by 3 out in the front, and then it's the first endpoint. So since we're going from 1 to 2, it's going to be f of 1. There's a coefficient of 1 in front of that. Plus, the second value gets a 4. So 4 times. And if we are dividing it up, if our delta x is 0.25, then the distance from 1 to the next point is going to be 1.25, right? So 4 times f of 1.25 plus, then the next coefficient in the pattern is a 2 times f of, and then 1.25 plus 0.25 would be 1.5 plus, then we have to have a 4 again. F of 1.5 plus 1.25 is 1.75 plus, and then we have to, the endpoint of our interval has to have that coefficient of 1 again. So f of 2.0. Okay, so there's our Simpson's rule kind of laid out for us. So now we can go ahead and plug our values in. So our area is going to be approximately equal to our delta x, which is 0.25 divided by 3. And then f of 1 is 1. 4 times f of 1.25. So you have to do, again, our function is our 1 over x, right? So 1 divided by 1.25 times 4. Okay, so that gives us 3.2. So again, we're just doing f of 1.5 times 2. That gives us 1.333. Then we do f of 1.75 times 4. That gives us 2.286. And then f of 2.0. And then that times 1 is just f of 2.0, which is our 0.500, or just 0.5. And then again, grab your calculator and do the math, and we get area is approximately equal to 0.693, woohoo, which we know is actually our exact value. Okay, so this is the closest approximation so far to the actual value. Now, of course, I want you to be thinking about something. Is that always going to be the case for any function? Is Simpson's rule always going to be the best approximation? And the answer is no, of course that's not true, right? It depends on what the function looks like. If we have a function that is sort of has a curve to it that looks parabolic, then it would make sense that Simpson's rule would be the best estimate, right? But not necessarily the case for all functions, so it does kind of depend on what the function looks like. Our final example in this section says that the graph of the acceleration a of t of a car measured in feet per second squared is shown. And I'm not sure why it looks like mine says example 10, because I know on your paper it says example 6. That's okay. Use Simpson's rule to estimate the increase in the velocity of the car during the 6-second time interval. Okay, so think about our relationship here. We have a graph of the acceleration. So if we want to estimate the increase in the velocity of the car, so first of all, increase means it should come out positive, right? If we want to find out the increase in the velocity, remember that acceleration is the derivative of velocity, right? So if we have a graph of the acceleration and we find the integral of it, then our increase in velocity would be represented by the integral of our acceleration, because acceleration is the derivative of velocity, so therefore velocity would be the integral of acceleration. So let's write that down. If we have a graph of acceleration, and again, we don't have a function now this time, we only have a graph to work with. The increase in velocity would be represented by the integral from 0 to 6 of the acceleration dt, right? And again, this is because velocity is the integral of acceleration. Acceleration is the derivative of velocity, okay? So the idea here is we would like to use Simpson's rule. We'd like to practice that one more time because I think that's the trickiest one to remember. And so if we're going to use Simpson's rule, first of all, we know that our n has to be even. And since we're going from 0 to 6, it seems like our delta x, 0 to 6, that would be a nice delta x, right? Because that would give us a delta x of 1. So our delta x is going to be equal to 6 minus 0, that's our b minus a, divided by 6, which is 1. And so we're going to be doing s of 6 here, approximating this using s sub 6, right? Simpson's rule with 6 segments, all right? And so our integral from 0 to 6 of a of t dt is going to be approximately equal to, sorry, didn't mean to make that look like an integral, s sub 6, which is going to be approximately equal to our delta x divided by 3 times, okay, now our lower endpoint is 0, right? So at 1 times f of 0, there's our coefficient of our first term, plus, then it has to be 4 times, and then the next spot is going to be f of 1, plus 2 times f of 2, plus 4 times f of 3, plus 2 times f of 4, plus 4 times f of 5, plus 1 times f of 6. Right? We always have to start with that 1, 4, and then end with that 4, 1 at the other end. And so now I'm going to have to use my graph to estimate the value of the function because I don't have a function to plug it into, right? But that's okay. I've got an x and a y axis, so I can do some estimating here. So plugging some numbers in here, my s of 6 is going to be approximately equal to delta x is 1 divided by 3 there. And let's see, f of 0. Well, that's 0. And 1 times 0 is still 0. Okay. Plus 4 times f of 1. Well, f of 1, again, this is 2, 4, 6, 8, 10. So it looks like, I mean, that's maybe a quarter of the way, so I'm going to call that 0.5 on my y-axis. So 4 times 0.5 plus 2 times f of 2 is at exactly 4. That's nice. Plus 4 times f of 3 is at exactly 10. Plus 2 times f of 4 looks like it would be at 13. 4 times f of 5 looks like it's at about 9. Plus 1 times f of 6, and f of 6 is back at 0. Okay, so then I do the math there. So my s sub 6 is approximately equal to 1/3 times 0 plus 2 plus 8 plus 40 plus 26 plus 36. Add those together, divide by 3, and we get our s sub 6 is approximately equal to 37.3. And if we're looking at what the increase in velocity is, then our units would be in feet per second. And so here's how we would use Simpson's rule and the points on a curve, a given curve of acceleration, to approximate an increase in velocity.